All right, on number 102. All right, it says a car is driven 15,000 miles a year and gets X miles per gallon. Assume that the average fuel cost is $1.55 per gallon. Wow. You know, about 4.5 years ago, that would have been true. That's how fast it's changed. No, now I'm lost because now I'm dreaming about $1.55 gallon gas. Find the annual cost of fuel C as a function of X and use this function to complete the table. Who would benefit more from a 1 mile per gallon increase in fuel efficiency, the driver of a car that gets 15 miles per gallon or the driver of a car that gets 35 miles per gallon? Explain. So, our function is for the cost. So the cost is going to be how much gas you buy times the price. All right, so how many gallons of gas times the price per gallon. So gallons of fuel times price per gallon. Well, they flat out tell us the price per gallon. Okay, $1.55, so 1.55. And if we drive 15,000 miles a year and we get X miles per gallon, well, then 15,000 divided by our miles per gallon gives us the number of gallons we have to buy. With me? All right. So multiply 15,000 times 1.55, so we get 23,250 X as our cost function. And I probably should have written it up there. X stands for what? The miles per gallon. I should have written that up there. I'll write it on here now. All right. Now, rewrite that as 23,250 X to the negative 1, and I can take the derivative of it. Using the combination rule, and I could have called this left side here, I could have called it C prime, but I called it dC dx. Usually we would say dy dx. Well, this one's dC dx because we're calling our function C instead of calling it y. So dC dx equals, then use the combination rule. So I'll multiply the exponent times the coefficient, so I get negative 23,250 x, and then subtract 1 from the original exponent. So negative 1 minus 1 is negative 2. And then if I rewrite that back as a fraction, it'll be a little bit easier to work with. So dC dx equals negative 23,250 over x squared. All right, so now we can fill in the table. We have x, and then c, and then dC dx. All right, so when x is 10, put a 10 into c, put a 10 in there, and c equals 2,325. And that would be in dollars. Since our price was in dollars, that'd be dollars. When x equals 15, put a 15 right there. So 23,250 divided by 15 gives us this cost. For the next one, put in a 20, we get this cost. For 25, we get this cost. And to nobody's great surprise, as your miles per gallon increases, your cost decreases. You could have guessed. Oh, I hope you wouldn't even have to guess. I mean, you just know that, right? If you buy your own gas, you know that. Yeah, I bought a gas guzzler right before prices went up. An Explorer. Oh, it's about 15, 16.
That's solid. I get.
Okay, you're dumber than I am. But see, I was driving some little car that got good gas mileage. I'm like, gas is practically free. I was going to the pump, pouring it out on the ground, you know. And then all of a sudden, the price quadruples, and I'm like, Bad idea. Okay. So filling in the cost line's fairly easy, right? Well, filling in the DC/DX line's pretty easy too. Okay? All we're doing now is we're taking the X and we're putting it in right there. So you'd put in a 10, square it, get 100, do the division. And what, by the way, what's DC/DX mean? All right, it means C prime, it means derivative, but in this case, what's derivative mean? It's a rate of change of the cost of the C function. It's the rate of change of the cost. Okay? All right? When x equals 15, you put a 15 in there, you square it, do the division, and so forth. Everybody with you on how to fill in the chart? All right, now, the rest of this. Oh, I didn't write it down. I'll write it down now. We're supposed to, who would benefit more from a 1 mile per gallon increase in fuel efficiency? The driver of a car that gets 15 miles per gallon, this guy, this genius, or the driver of a car that gets 35 miles per gallon. So, when's the rate of change of the cost changing the most? That's the guy that needs an extra mile per gallon. Okay, because it's going to have a bigger effect, isn't it? Because the rate of change is bigger the lower your miles per gallon is. All right, point being, look, there's not just a tremendous difference either in the cost per year or the rate of change of the cost between 35 and 40, is there? Much bigger chunk of change between that cost and between those rates of change. Okay? So the lower the miles per gallon, the more desperately you need to get a more fuel efficient car if cost matters. Okay? So the 15 mile per gallon driver needs to trade in his Explorer for a no, I would die before I drove a Prius. Sorry. You know what I really want to get? I'm going for it, an Expedition. I know. I know that's a worse choice. Okay, for a tin can. But when prices go back down to $1.55, I'm pouring the gas out on the pavement again. And I'm just going to leave my car running at all times. Yeah, during the night, so that way it's nice and warm when I get in it the next day. All right. What else you want to say? 89. All right, let's see. What are we doing here on 89? Says find the average rate of change of the function over the given interval, and then compare this average rate of change with the instantaneous rates of change at the end points. So, average rate of change. Think of it like this. No, that's not the way you write it. This will serve you well. Okay? Now, the x2 minus x1. Let's do that first. Well, there they are. That one's x2, that one's x1. Okay? Now, to get the y2 and the y1, if that one's x2, wouldn't y2 be the value of the function for that particular x-coordinate? So y2 is f of 2, or g of 2, or h of 2, whatever they name the function, c of 2. Okay? minus, and then y1, well, that's x1, so y1 will be the value of the function for that x coordinate. So in this case, f of 1. Does that make sense? Everybody able to set that up for the average rate of change? Okay, well then we just do the math. There's f. So if we want f of 2, that'd be 2 times 2 plus 7, minus f of 1 would be 2 times 1 plus 7. In the denominator, 2 minus 1 is 1. So let's see, 2 times 2 is 4, plus 7 is 11. 2 times 1 is 2, plus 7 is 9. So 11 minus 9, which is 2, over 1, 2. So the average rate of change from t equals 1 to t equals 2 is 2. 2 what? I don't know. 2 feet per second, 2 miles per gallon, 2 something. Okay, they didn't tell us the units, so we don't know 2 what's, but it's 2 something per something. All right, now, the instantaneous rate of change. Find the derivative, because the derivative is the instantaneous rate of change. Well, if that's our function, then doesn't f prime of t just equal 2? All right, if I've got f of t equals 2t plus 7, I take the derivative of each term. So f prime of t, the derivative of 2t. This is a combination rule. That's like a t to the 1, exponent times coefficient. T, subtract 1 from the exponent. Then the derivative of 7 is 0. The derivative of a constant is 0. So you got to remember this. What's t to the 0? What's anything to the 0? It's 1. So 2 times 1 is 2, and then plus 0. So 2. So f prime of t equals 2. So we were supposed to compare, well, so the average rate of change equals the instantaneous rate of change. There's nothing else for me to do. I can't find f prime of 2. Well, I can. Maybe I should have written that down. Since f prime of t equals 2, guess what f prime of 2 equals? 2. Guess what f prime of 1 equals? 2. Okay? Mm-hmm. Think of this on a graph. If we graph y equals 2x plus 7, isn't the rate of change between any 2 points 2, because 2 is the slope of the line? Right? Slope of a line, slope never changes. It's constant. So if this represents, rate of change, well, if the derivative represents rate of change, and the rate of change is a constant, the slope is a constant, then no matter where you find the rate of change, it's going to be 2. 91. All right, same directions. So we find the average rate of change. So y2, since our second x coordinate is 2, so that'd be f of 2 minus y1, since our first x coordinate's 1, f of 1, over x2, 2, minus x1, 1. Then we find f of 2. Well, there's f, so f of 2 would be negative 1 over 2. Then we get f of 1. Well, again, there's f, so that'd be negative 1 over 1. That's how I get that line. 2 minus 1 is 1. All right, so I've got a negative 1/2, and then minus a negative means plus. So I've got a negative 1/2 plus 1. So I've got 1/2. So the average rate of change is 1/2. Any questions on getting the average rate of change? Okay. Now, to get the instantaneous rate of change at an end point, we need the derivative, because the derivative is the instantaneous rate of change. So that negative 1 over x, I'm going to rewrite as negative x to the negative 1, because now I can use the combination rule. So exponent times coefficient. Negative 1 times a negative 1 gives me a positive 1. X, subtract 1 from the exponent. Negative 1 minus 1 is negative 2. So f prime of x equals x over negative 2. And what's almost always a better version of x over negative 2? Or x to the negative 2? 1 over x squared. So my derivative is 1 over x squared. Now that I know the derivative, I use it as a formula to find the instantaneous rate of change anywhere I want to. So I'm supposed to find it at each endpoint. So I need to find what the derivative equals when x equals 1, and then I need to find what the derivative equals when x equals 2. That means I need to find f prime of 1, and then I need to find f prime of 2. And that's f prime. Make sense? The answer to 58. Yeah, don't you hate it when you don't get an answer? So what do they ask us? To find find all the points where the graph has a horizontal tangent line. So you know that derivative equals slope of the tangent line, so you find the derivative. You know that if the tangent line's horizontal, that the slope is 0, so you set the derivative equal to 0 and you solve it. Only problem is there's no solution to that because we're working with real numbers. So no solution. So that particular function does not have any horizontal tangent lines. Yeah. 96. All right, what are we doing on 96? It says in exercises 95 and 96, use the position function s of t equals negative 4.9 t squared plus v sub 0 t, that means initial velocity, times t, plus s sub 0, that means initial position, for free-falling objects. So for 96, they tell us to estimate the height of a building, a stone is dropped from the top of the building into a pool of water at ground level. That's the way I would estimate the height of a building. How high is the building if the splash is seen 6.8 seconds after the stone is dropped? All right, so we're using this as our position function. Why are we using that as our position function? They told us to. So that's our position function. Now, we don't know the height of the building because the initial position of the stone is the height of the building, isn't it? So that has to stay an unknown. Now, since it says the stone is dropped, the initial velocity of anything that's dropped is 0. You didn't fire it, you didn't throw it, you didn't sling it, you didn't use anything to give it an initial velocity. So V0 is 0. Okay? So we can rewrite our position function, 0 times t is 0, to get that one. You with me so far? Now, they tell us that the stone hits 6.8 seconds after it's dropped. Okay? So if I replace t with 6.8, I'll replace it there with 6.8. I'll replace it there with 6.8. You did not see that. I now have the position function for when t equals 6.8. Now, what else is happening at 6.8 seconds? Well, it will because it stops, but what's its position? It's at 0. It hits the ground. Okay? So if the top of the building is the initial position, then, I mean, you don't have to do it this way, but do it this way. Make ground level 0, and then the height of the building is whatever the height of the building is. Okay? So you dropped it here, and the little stone is screaming all the way down. Ah. Then at 6.8 seconds, that's when it hits the ground. So the position, which this represents, the position at 6.8 seconds is 0. Okay? So, get out your calculator. You think, all right, so I need to take 6.8 and square that, and then multiply that times negative 4.9. So I skipped this step, I don't know why I did. So I get negative 226.576 plus S0, the initial position, equals 0. So add 226.576 to both sides, and you get S0 to be 226.576. And let's see, how did I know that was meters, other than I know that's the one for meters? I guess the only way I knew that was meters is I knew that was the one using, that's the meter one. The feet one is negative 32 instead of negative 4.9. Yeah.
I use the feet, so it should just give me the same answer.
Yeah. Yep. Yeah, it should. Yeah, if you use the feet one, you should get the same height just in feet. All right, does that help? Any others? We good? All right.